Part 3 of the lecture discusses numerical ages, which are also called absolute ages. Numerical ages for rocks, fossils, and sediment are determined through something called isotopic dating. This is also called radiometric dating, and it's a technique for calculating numerical ages using the ratios of radioactive elements and isotopes to their decay products. Geochronology is the overall study of numerical ages of the rocks. Radioactive decay is defined as the change of an unstable parent isotope into a more stable daughter isotope. And the concept of half-life is useful in radioactive decay because it is the time that it takes for half of a group of atoms to decay from parent to daughter. It's important to note that the rate of decay of any isotope is constant, and the number and ratio of parent isotopes to daughter isotopes can give us a measure of how much time has passed. For each half-life that has passed, the ratio between the two changes in a predictable way. So on the diagram to the right, we have two plots or two different variables plotted on a graph of the number of atoms versus the number of half-lives. And below it we have the same representation, but for your benefit, visualized in terms of these different blocks. So at time 0, or at 0 half-lives, we have 16 parent atoms and 0 daughter atoms. This is also can be thought of as 100% parent and 0% daughter. After 1 half-life, we've divided the parent isotope by, or we've multiplied it by 1/2 or divided it by 2 only one time. So we get 8 parent isotopes and 8 daughter isotopes. This would yield a ratio of 50% to 50% or of 1 to 1. Now, if we have another half-life pass by, had 2 half-lives, then we've multiplied the original parent 16 by 1/2 twice. So we've in effect multiplied it by 1/4 or divided it by 4. This is 16 divided by 4 equals 4. And knowing that the number of parents plus the number of daughters must always equal 16, because we have 4 parent isotopes left, we must have now increased the amount of daughter isotopes in an equal amount, in a proportional amount, to yield 12 daughter isotopes. And if we go on to half-lives 3 and 4, then we produce the same pattern. It's important to know that the parent never decays exactly to 0, and the daughter never grows exactly to 16 or to 100%. We keep dividing by half over and over again for eternity. Different isotopes are useful for different lengths of time. So when we're dating geologic materials, we want to choose the correct isotope or parent isotopes or parent-daughter combination to yield a good or precise result. And this is based on the different half-lives. So, for example, samarium and neodymium have half-lives of 106 billion years, and they're present in garnet and mica. Rubidium decays to strontium over the course of 48.8 billion year half-life, and it is present in a lot of potassium minerals. Uranium decays to lead over 4.5 billion years and is present in zircons. Potassium decays to feldspar over the course of 1.3 billion years and is also present in potassium-bearing minerals. Uranium-235 decays to 207 lead over the course of 713 million years and also is present in uranium-bearing minerals. There are several steps used to isotopically date geologic materials, and the first involves collecting the appropriate samples, then separating the datable materials, most often minerals, and then extracting the parent and daughter isotopes from those minerals. then finally analyzing the parent-to-daughter ratio. The instrument on the bottom is known as a mass spectrometer, which ionizes certain isotopes through a laser or introducing a gas, and sends those isotopes through a chamber that, or sends those ions through a chamber that allows them to count the different ions based on their mass. So if we were dating from uranium to lead decay, some of those isotopes of uranium would be collected after being separated due to their mass, and some lead isotopes would be collected after separation due to their mass. And then from the computer data collected, we would analyze those parent-to-daughter ratios. It's important to understand what isotopic dates actually mean. Well, they represent the closure temperature, or the temperature below which isotopes can no longer freely move in and out of a crystal, for example, a mineral. So rock dates are from this point in their formation. Most dates come from igneous rocks, and metamorphic and sedimentary rocks, we do not often know when the minerals first crystallize. But we can use the relative dating to bracket the ages of rocks on which isotope dating is not possible. So all elements of dating are combined, which include relative dating, fossil evidence, stratigraphic columns, and isotopic dating to create a geological timescale. There have been many estimates over the course of human history to understand the age of the Earth. Lord Kelvin in the 19th century estimated a 20 million year old age based on a cooling rate of the Earth. Hutton and others used uniformitarianism to suggest a much older Earth. And nowadays we understand that Earth is about as old as 4.4 or 4.5 billion years based on Earth-based minerals dating through things like uranium lead systems or meteorites